Today we're going to be talking about voltaic cells. When you take a look at the reading, chapter 21, section 1 in our textbook, we describe a little bit of what we already know about oxidation and reduction in terms of half reactions, an oxidation half and a reduction half. And from there we get into an electrochemical cell. And I'd like to make a diagram, an example, to support this. Let's go. In an electrochemical cell, we have two metal electrodes connected in a circuit. One of the electrodes is made of one metal, the other electrode is made of a different metal. Each metal is going to have a different, what's called a reduction potential. The reduction potential is the relative ability of a reduction reaction to accept electrons or to be reduced by electrons. So in our example, we're going to hook up a zinc electrode to a copper electrode. Our zinc electrode is going to be suspended in a solution. This solution is going to contain zinc sulfate, so zinc 2+ ions, and sulfate, SO4 2- ions. Our copper 2 sulfate electrode will be suspended in a solution that contains copper 2+ ions and SO4 2- ions. Let's look up the reduction potential of each half reaction. When zinc ions in solution accept electrons to become zinc metal, we compare that value to the standard hydrogen electrode, which we can find on page 667 and table 21-1. So compared to the standard hydrogen electrode, the reduction potential of a zinc ion accepting electrons is negative 0.7618 volts. So it is less likely than a hydrogen electrode to accept electrons. It's more likely to be oxidized compared to that standard hydrogen cell, which is 0. The reduction potential of copper 2+ to become copper metal has a positive value. So it's likely to be reduced by electrons compared to the standard hydrogen cell. This means that of these two metals, the metal that has a greater reduction potential will be reduced. The metal with the lesser reduction potential will be oxidized. This means that electrons will flow from our oxidation half reaction to our reduction half reaction. What does this look like? Well, this means that our zinc electrode, which is made up of billions and billions of zinc atoms are going to be oxidized to form zinc 2+ ions in solution. So our zinc electrode is actually going to be diminished. It's going to get smaller. It's going to get eroded. It's going to get used up. On the other hand, our copper ions in solution are going to accept these electrons. And they're going to add another layer of copper atoms on top of this copper electrode. Our copper electrode will increase in size as copper ions are reduced and the metallic lattice is extended. This is why batteries eventually run out. Your oxidized half reaction, eventually you either use it all up or there just isn't sufficient atoms left to be oxidized to provide enough current to power your device. So as your battery gets weaker and weaker, less surface area is exposed, fewer atoms are being oxidized, fewer electrons are passing through the wire, eventually your battery dies. When you recharge a battery, essentially what you're doing is you're hooking this up in reverse to an external power supply and you're forcing the opposite reaction to occur. But more about that when we discuss electrolytic cells later on. Now there's a problem here. As zinc ions build up in solution, a net positive charge develops in this half cell. And as copper 2+ ions get consumed on what is our cathode side here, the side accepting electrons, a net negative charge arises. Sulfate ions remain, but the copper 2+ ions are removed to form copper metal, and negative charge is moving from left to right. This is a problem because electrons are not likely to leave a region of positive charge. They're attracted to it. Electrons are not likely to go to a region of negative charge. They're repelled by it. So this is a problem. This is a problem solved by the final component, which is called the salt bridge. The salt bridge allows for the free flow of zinc ions from a region of positive charge to a region of negative charge. And this will occur spontaneously. This connection between the two half cells, we're going to get zinc ions in solution passing through our salt bridge into the cathode side. Positive is attracted to negative. They'll freely flow. Conversely, sulfate ions will flow through the salt bridge towards the anode half reaction because it's attracted to the positive charge. So sulfate is attracted to the positive, the zinc ions are attracted to the negative, and we end up with an exchange of ions back and forth between the salt bridge. And this serves the purpose of neutralizing the charge. And that allows for electrons to flow freely from one electrode to the other without that buildup of electrostatic charge inhibiting the reaction. So if you'll recall, copper has a greater reduction potential than zinc, which means that it is more attractive to electrons than zinc. It will strip zinc of its electrons and draw them towards itself and be reduced. Zinc with lesser reduction potential is more likely to be oxidized. So we have our oxidation half reaction, the zinc being oxidized, and our reduction half reaction. When we're calculating the potential of our cell, our electrochemical cell, it's equal to the reduction potential of our reduced half reaction. So that's positive 0.3419 volts. Subtract the reduction potential of our oxidation half reaction, which is negative 0.7618 volts. When we subtract these two, we get 1.1037 volts. And that is the cell potential of this electrochemical cell. All right, recall in our previous reaction, we had two half reactions occurring. We had a zinc metal atom being oxidized into zinc ions in solution, and we had copper 2+ ions being reduced into copper metal atoms. This was our oxidation half reaction, and this was our reduction half reaction. When we're writing cell notation for the electrochemical cell that we just created, we list the reactant and product of our oxidation half reaction, separated by a single line. Then we have a double line representing the salt bridge. We have our reactant and product from the reduction half reaction on the right-hand side of our salt bridge. All right, in cell notation, we list the reactant and product of our oxidation half reactions on the left. We list the reactant and product of our reduction half reaction on the right, separated by the lines as we see here. That's cell notation. All right, let's do practice problem number 1. In practice problem number 1, we're given that two possible half reactions can occur. To figure out which one is more likely, we need to look up these values in our standard reduction potentials table, table 21-1, on page 667. When we look up the reduction of platinum by 2 electrons, we get a reduction potential of positive 1.18 volts. When we look up tin 2 plus being reduced into tin atoms, we end up with a negative 0.1375 volts. The larger of these two values is the reduction reaction that will occur. The smaller of the two values is the reduction that will not occur, but rather it will be an oxidation reaction. Recall, the reduction potential is the relative ability of these ions to be reduced by electrons. Platinum is much more likely to be reduced. Tin is much less likely to be reduced. You can think of these as a ranking. Platinum is ranked much higher than tin, which means that it will be reduced compared to tin. The reduction potential of our cell is equal to our reduction half reaction value, its standard potential, subtract the standard potential of our oxidation half reaction. So in this case, our electrochemical cell has a cell potential of 1.32 volts. But that's not the only thing this question asks us for. It also asks us for a balanced equation. So let's do that. Notice we flipped the reduction of tin to represent its oxidation. So rather than having tin be reduced, because it's the smaller of the two values, when these two metals are exposed in an electrochemical cell, this will be the oxidation half reaction. So we flip this. Now, when we add these two half reactions back together, the first thing we look for is, do our electrons lost and gained match? If they don't, we would need to multiply each of these half reactions by a factor that would make these electron values to be equal. In this case, 2 and 2 is equal, so no factors are needed. When we add these together, we get our our balanced reaction. If you're looking for another way to calculate cell potential, recall that the cell potential of platinum was 1.18 volts in the positive. When we flipped the reduction of tin to represent its oxidation, we also flipped the sign. If we flip the reduction of tin to represent its oxidation and flip its sign, when we sum these values, we end up with the same value. Indeed, this is why we subtract the reduction potential of the oxidation half reaction to flip that sign, to represent it as oxidation rather than as reduction, because that negative value represents its reduction potential. Finally, we have to represent this as a cell potential using cell notation. Let's describe this electrochemical cell using cell notation. Is this correct? No, this is not correct. We want to make sure that we have the oxidation listed first and the reduction listed second. So let's try this again. Much better. Because remember, we want to list oxidation first, and we want to list reduction second. In practice problem number 4 on page 672, we are asked whether or not this reaction will occur spontaneously. To determine whether this occurs spontaneously, we need to describe this in terms of its half reactions. Let's do that. In this case, tin from an oxidation state of 0 becomes tin 2 plus with an oxidation state of plus 2. In the process, it lost 2 electrons, which we can represent using this half reaction. In this case, the simplest way to describe this half reaction is a copper 1 plus ion accepts an electron to become copper metal. Let's describe this electrochemical cell. In this case, our reduction half reaction is the copper 1 ion being reduced into copper metal. Take a look on page 667. Can you find the reduction of copper 1 into copper atoms? Positive 0.521 volts. We look up the oxidation, or the reduction potential, excuse me, of tin. It's our oxidation half of the reaction. It has a negative 0.1375 volts. We do a little math. Reduction potential of the chemical reaction that we see above is 0.659 volts. Now, the reduction potential of this cell describes with what force electrons are being pushed from the oxidation half reaction to the reduction half reaction through the wire or through the connection. If the cell potential is positive, 0.659, it is, the reaction will be spontaneous. This is a spontaneous reaction because we have that positive value in front. If this cell potential was negative, however, this would not be a spontaneous reaction. All right, and that's it. Good luck. Let me know if you have any questions or comments. Thank you very much for your time. Good luck. Take care. Bye now. See you again soon.